Let's take a look at ellipse tangents. There's a calculus understanding of the slope at a point that you can get with implicit differentiation, but that is quite different from the geometric understanding of tangents, lines that intersect the ellipse at a single point. But this geometric definition offers some more interesting properties than just the slope. So let's take a look at the foci and the single point of intersection. A natural question to ask is, what exactly makes this point on the ellipse special? To answer that, we're going to want to go on a bit of a tangent to talk about distances in ellipses and Heron's problem. A common definition for an ellipse fixes a length and two foci, then takes the locus of points whose sum of distances to the foci is that fixed length. So that means for a point whose sum of distances to the foci is not that fixed length, the point is not on the ellipse. Seems simple enough, but we can get a little more information from this. There are two general areas of the ellipse, inside and outside. If you take a point inside the ellipse, we can extend one of the lines to the ellipse and then apply the triangle inequality on the extended triangle. With some clever distributions of lengths, the sum of the distances from the points inside the ellipse will be less than the fixed sum for the ellipse. For points outside the ellipse, we can make a similar argument, this time with a triangle outside the ellipse, showing that the sum of distances to the foci are greater than the fixed length for the ellipse. Okay, with that, the two regions of inside and outside can be classified by the sum of the distances to the foci. If it's equal to the fixed length, the point is on the ellipse. A distance less than the fixed length puts the point inside the ellipse, and a greater distance places the point outside the ellipse. With this focus on distance, we can make a cool observation about the tangent line. There are no points inside the ellipse. Everything is outside the ellipse, with a single exception, which is the tangent point on the ellipse. What this means is that the point on the tangent line is the special point that minimizes the sum of the distances to the two foci. Now we can finally move on to Heron's problem. Given 2 points and a line, Heron's problem asks, what is the shortest path between 2 points that also touches the line? For this problem, we need some even more clever work. We know that we'll want 2 line segments and a point because there has to be at least 1 point on the line, and the shortest distance between points is a straight line. But how do we know which point? Well, for that we can cleverly create a reflection of one of the points over the line. With this, we know that the distance from the point on the line to the reflected point is the same as the distance to the original point. And now we can see that we want a straight line, not something bent. With this, we can see that the point on the line, minimizing the sum of the distances to the foci, will have that the lines to the foci form the same angle to the line. However, this isn't the most satisfying answer we can get. What might be easier to look at is the normal line, the tangent to the tangent. Splitting the line into two 90-degree angles, we get the other interior angles are complements to the same angles and are therefore equal. So the normal line here is the angle bisector of the triangle formed by the foci and the point of tangency. So if you want a tangent, take an angle bisector and a perpendicular line. And you can thank Heron's problem for this geometrically normal way of finding the tangent.